Question number 2 says a box with an open top is to be constructed from a square piece of cardboard 3 feet in width and length. So we're going to have a square piece of cardboard that is 3 this way by 3 this way. And we're going to cut off the corners of the rectangle. So we're going to cut off this corner over here and this corner over here and so on. And when we do, what's going to happen is we're going to create these lines on which we're going to fold the shape. When we fold the shape along those lines, that's going to create a box. So what we need are some dimensions. We don't know what we're cutting off the corners, so let's call that X and that X on each one of the sides because we are cutting off squares. Those X's are going to become the height of my box when I fold it upward. Now, from there, if we cut off 2 X's, that makes the width of this, the dotted line section, 3 minus 2x. It also makes that the side here and here and here as well. So those dotted lines are all 3 minus 2x. So now, once we know that, we're trying to make the largest box that we can, and we want to justify that answer. So we're trying to maximize our volume. So the volume of a box is length times width times height, and that's what we're trying to maximize. Now, the length and the width of the dotted lines, so that's going to be 3 minus 2x for the length and 3 minus 2x for the height, or for the width rather, and x for the height. So that could be my function. It's one variable, but I definitely want to try and simplify that first. So multiplying that all out, 3 times 3 is 9 times x, so we get 9x. Minus 6x is minus 12x, and times another x is minus 12x squared. And then 2 times 2 is 4x. And we're going to go ahead and multiply that by 1 more x to get 4x cubed. That is going to be my function. So from there, the next thing I need is my derivative. My derivative is pretty simple here. 4x cubed becomes 12x squared. Negative 12x squared becomes minus 24x. And then 9x just becomes plus 9. So then I want to find my critical values. To find my critical values, we need to set that equal to 0. So first off, they're all divisible by 3. So when I divide them by 3, I'm going to get 3 times 4x squared minus 8x plus 3. I need the factors of 12 that total 8. Those are 6 and 2. So that means we're going to have 3. I know the first parts need to be 2x and 2x to make 4x squared. I know the second need to be 3 and 1. And this makes 6 and this makes 2, which means if I do minus and minus, they're both going to equal what I need them to be. So now my critical values are 3 halves and 1 half. So when I have 2 critical values, the problem is I don't know which one is a min and which one is a max. So the way we do that is off of the second derivative test. Our second derivative is going to be off of the original first derivative, 24x minus 24. So if I plug in my individual values, if we plug in 3 halves first, 24 times 3 halves is 36 minus 24, which makes 3 halves greater than 0, which makes it concave up, which makes it a minimum. And if we do 1 half, half of 24 is 12 minus 24, which is less than 0, which makes it concave down. So 1 half is the maximum. Now, common sense would dictate that 3 halves has to be the minimum. If you cut off 1.5 from each side, you'd cut off a collective total of 3, and there'd be no cardboard left. So 3 halves has to be the minimum, 1 half has to be the maximum. So now just one more thing I have to do is make sure I've actually answered the question rather. It says find the largest actual volume. So I need the volume here. Well, I know the x value is 1/2. Plugging it back in, my height would then be 1/2. My width would be 3 minus 2 1/2. So 3 minus 2, or 3 minus 1, so 2. And also another 2. That means my dimensions are 2 by 2 by 1/2, making my volume half of 4, or 2 cubic feet. And we don't have to justify because we already did in finding it. So this is my answer for the volume.